I'm Cyan. I'll be talking about our work cocktail, a multidimensional optimization for enabling model serving using ensemble learning in public cloud. I have my co-author here, Jashwant Gunasekaran, and let's get started with. I'll thank my previous speaker. They already motivated machine learning for us. It's been everywhere. All of us being students, being small-scale businesses and large-scale businesses are using machine learning very rapidly. And we typically take a lot of data, train it, and build different models. But building these models, serving them is an expensive idea because it takes a lot of resources. So the solution that people have come up with to try these things are model serving in public cloud, like Amazon or Microsoft or Google's offerings. And most of us, being customers, we actually send these requests of inferences to the public cloud. We have a SLO agreement. We expect them to be done within a certain amount of time with some accuracy, and we choose they give us the resources, the models to get our requests done. And how do they do it? In public cloud, they typically provide us VMs or containers to deploy these things. So there are challenges to all of this. First, all these resource provisioning takes some time. On top of that, there is the model that is being served there, which is doing the inference. That also has some latency to give us the results. And if you look at the model serving latencies and the cost issues, what we see is there are typically two types of issues. One is the resource type, what we are doing, and there's a provisioning latency because of that. And what resource type you're using, that is associated with some cost. Then there is the model type. If you are using a bigger model, you will need more resources, you will need more time, and that will incur some cost. You need more accurate results, you need better models, better resources, and that causes the cost. At the end of the day, it's all about the money. So it's a lot of work actually and a lot of good community collaboration to reduce the provisioning time of these resources. However, the latency and accuracy has been a big challenge and actually an important aspect. We have listened to several talks in this conference and other places that real-time applications like Netflix or your Amazon shopping, all these are very accuracy and latency sensitive. The typical recommendations you're getting is very sensitive to this accuracy and latency. So how do we actually improve the accuracy of these model servings in public cloud, especially with a high accuracy and low cost system? Turns out we already have solutions which try to do this. There is Infast and Clipper, which are one of our baselines. We try to see that they're trying to ensure low latency or they're trying to increase the accuracy. But all the threefold optimization is kind of missing. It's obvious because once you try to go for high latency, you need more resources and, of course, more cost. What we try to do is to minimize all or optimize all three of them together. So bring high accuracy, low latency, and low cost. So how do we do it? So how do you get more accuracy? Again, turns out machine learning community has solved this problem long time back. There is ensemble learning. You take a lot of small models, small learners, combine them together, you get a better model than the larger model. But how do we do it? Fairly straightforward, nothing complicated here. We have a host server that is taking on request. We have a lot of lists of models, and we just send our request to this host server. Host server takes the SLO into consideration, sends these to multiple such models to serve the request. And finally, we have an aggregator which does something like adaptive or gradient boosting or something like that to aggregate it, or a simple majority voting. And finally, we get our result. But when we are trying to combine a lot of such models, it demands more resource. We go back to the first problem again, more resources, more cost. How do we solve it? How do you reduce the resource footprint? A slight background here. So how much do you need more resource? So to just increase 2% in your accuracy, especially in the vision side, 2% increment, you need twice the more parameters. And is it worth it? Is there a way we can bridge this 2% accuracy gap? and needing like twice more resources, can we reduce it down? And that increases cost, and hence can we reduce the cost? How do we perform better ensemble learning? So we tried to do a study. We had a lot of, we stick to the vision task for at least for the study part. We have a list of models, and we took the top 12 most frequently used models, chose a baseline, this is the most accurate model, and any model which has less resource footprint than that, we took them, combined them together, did a majority voting, and we saw we got more accuracy. Target achieved, more accuracy done. Now, because we are combining a lot of models together, the accuracy, the latency of the largest of them becomes our bottleneck latency. So we saw that with the ensemble, we got a quite good accuracy in terms of latency as well as accuracy. We got very well. However, the problem is cost. Now we, instead of doing one model, we just brought in 5, 6, probably 10 models. And for deploying it in a public cloud environment, let's take the Amazon on-demand instances, our cost shot up about twice. So for doing ensemble learning, so how do we reduce it? We thought we could use the intermittent instances that is already available by the public cloud service providers. For this example, the Spot instances by Amazon, and that actually reduced our cost significantly. So these transient instances are significantly cheaper. The problem is they are intermittently available. They can be revoked at a short notice, but this can reduce our cost significantly. So now the problem is, how do we bring them together? So we have, let's say, take a larger model. For each of the large model, for example, NASNet large, we had to ensemble 10 models. And we thought, do we actually need so many models to be ensembled? Is there a way we can reduce the resource footprint by reducing the number of models that we're choosing to do the ensembling? And more importantly, because we have decided to use Spot instances, can we handle the instance failures? So the first solution we came up with, let's do something static. Let's chop the number of models that we select by half. And no surprise there, the accuracy shot down significantly. So how do we solve it? How do we dynamically select a model when there is requests are incoming, SLOs are changing, and all that? So we took the inspiration from multiple data sets. We did a thorough study and realized that not all models are built equally. Surprise. Then most of the models have better accuracy on some classes, bad accuracy on other classes. For example, let's take MobileNet, one of the networks that runs on your phones. For detecting in ImageNet, detecting slug, it does very accurately. But when it comes to Quill, it kind of performs really bad. So we thought, let's build a dictionary. Let's leverage this, try to build a dictionary of accuracy of each class for each model. Now, that can help us in deploying and doing a weighted selection of whatever classification we're doing. So now the cocktail design is pretty straightforward, very simple. We built this class-wise dictionary. We did this weighted selection for each of the inference requests we are doing. Some of the models have more weightage than other. Then we do have an aggregator which takes all these inferences, weights them, aggregates them, does a majority voting, and voila, we have our solution. So to be just a bit more formal here, we took our matrix to be 2 matrices. One of them is accuracy over latency. We are trying to maximize that. And on top of that, we are trying to minimize the instant cost we have. And we are trying to do a joint optimization in this front. Now, is there a way we can know what models to select? We cannot select this model a priori. We don't know what kind of inputs we are getting. And obviously, finding the best set of model is a very hard problem. But is there a way we can actually select a lot of models and drop some of them when we are doing the inference? Turns out that is a bit more easier. And what we decided is we just did a coin toss model, assuming that we have n biased coins. What is the minimum number of coins required to get the probability that whatever your accuracy is? And we just modeled it through the simple coin toss model and figured out what is the minimum number of models we actually require to satisfy the SLOs. Combine that with our previous selection, we actually had a dedicated pool of models or the dedicated pool of resources deploying each kind of models, maybe it MobileNet, maybe it ResNet and all of that. Then we have, per model, we have scaling facilities so that if we get a request where we need more models of some type, for serving our request, we can scale them properly. And then we have fault tolerant because we are deploying each request into several models. If one of these instance types goes down, let's say one of the instance serving one kind of model goes down, there are other 5 or 6 instances which are running different models, and we will still get an ensemble accuracy. So accuracy will be hit for a second or two. As soon as a new instance comes up, we are good. So just to bring it all together, we have a class-wise accuracy directory, we have a weighted majority voting, we have dedicated pool of resources for each kind of model, we can scale each of the resources per model, and we are fault tolerant. To evaluate this, our setup, we took 3 of the prior works, InFast Clipper and Clipper X, where Clipper X is trying to trim down this model one by one instead of we doing it dynamically. And we tried to set it up in Amazon Web Services. And we did ImageNet for the vision models and the sentiment analysis for the language model. So result, of course, because as I have explained, Cocktail actually incurred 32% less cost, and we got state-of-the-art accuracy as well, and it can actually trim down the number of models by 50% compared to the previous state-of-the-art while doing the ensembling. On top of that, sometimes it gets us more accuracy, about on an average 1.2% more accuracy. And because we are doing an ensembling and we are limited by the largest model in the ensemble, our latency goes down significantly, probably by 2x. On top of that, because we are talking about failures, given the premises we are using, the Cocktail quickly adjusts and quickly scales to the number of models required, number of resources required, and on an average uses 5 or 6 models to give us about the same accuracy as what we need to if we had aggregated 10 models together. On top of that, at times when some of the instances are taken out, we incur minimum accuracy loss. At worst case, we have actually suffered a 0.7% accuracy loss. And we typically compromise accuracy at times, but we try to bring it back as soon as possible whenever we have another instance available. Summarizing, we had the 3 goals. One is the higher accuracy, lower latency, and low cost. And we try to deploy it. The code is open source, and I would like to thank my co-authors, my collaborators, and the code is open source. You can all use it. With that, I would like to conclude my talk. Thank you, and I would invite my co-author Jashwant on the stage for the QA sessions.